Hello there, and welcome back to Science for Sleep. Tonight we are going to explore something that should not be possible. Not in the sense that it is difficult or unlikely, in the sense that it violates, at a fundamental level, every intuition about reality that you have built up over a lifetime of living in the ordinary world. Every assumption you hold about what things are, where they are, what causes what, and how the universe behaves when you are not looking at it. Tonight, we are going to explore quantum physics. Not the quantum physics of textbooks and equations, the quantum physics of what is actually happening right now at the level of the atoms that make up the air you are breathing, the mattress beneath your body, the neurons firing quietly in your brain as you listen to these words. The universe at its smallest scales does not behave the way the universe at human scales behaves. It does not follow the rules that centuries of science, built on the observation of things large enough to see and touch and measure, had established. It follows different rules, stranger rules. Rules so counterintuitive that the physicists who first discovered them spent decades arguing about whether they could possibly be true. They are true, and tonight, in the quiet of wherever you are listening from, we are going to let them slowly unfold. Tonight, where are you listening from? Is the room dark around you? Is the world outside your window still? Then the quantum world is already present with you. In every breath you take, in every surface you can feel, in the light, if there is any, that is reaching your eyes right now. So find a comfortable position. Let your body grow heavy. Let the thinking mind begin, slowly, to release its grip. And let's go somewhere very small and very strange together. Let's begin. To understand quantum physics, you have to first understand what it replaced. For most of the history of science, the universe appeared to be a machine, an extraordinarily complicated machine, governed by precise mathematical laws, but a machine nonetheless. If you knew the position and velocity of every particle in the universe at a given moment, the argument went, you could, in principle, calculate the entire future of the universe from that moment forward. Everything was determined. Everything followed from everything else in an unbroken chain of cause and effect, stretching from the beginning of time to its end. This vision of the universe was so compelling and so successful at predicting the behavior of everything from falling apples to orbiting planets to the flow of electricity through wires that it dominated physics for more than 2 centuries. It was called classical mechanics, and it worked magnificently for everything that could be seen and measured and touched. The problems began when scientists started looking more carefully at things they could not see, at the behavior of light, at the structure of atoms, at the way hot objects glow, at the tiny specific colors of light that different elements absorb and emit. The classical machine could not account for these things. Its predictions, when applied to the very small, were not merely imprecise, they were catastrophically wrong. The resolution of these failures, worked out over the first 3 decades of the 20th century by a generation of physicists whose names are now among the most celebrated in the history of science, was quantum mechanics. And the picture of reality it painted was nothing like the machine that had come before. The first, and perhaps most fundamental discovery of quantum mechanics is that energy is not continuous. It comes in discrete packets called quanta, a word derived from the Latin for how much. This was the insight of Max Planck, a German physicist who in 1900 found that he could make sense of the way hot objects emit radiation only by assuming that energy could not take any arbitrary value, but only specific, discrete ones, separated by gaps. He called this assumption a mathematical trick and expected it to be replaced by a more physically sensible explanation. It never was. The discreteness of energy turned out to be a deep and unalterable feature of the universe. Albert Einstein extended Planck's insight in 1905 when he proposed that light itself was not a continuous wave, but a stream of discrete packets, which he called light quanta, and which we now call photons. Each photon carries a precise quantity of energy, determined by its frequency. This was not simply a mathematical convenience. Einstein was proposing that light, which had been firmly established as a wave by 2 centuries of experiments, was simultaneously a particle.
This idea was so radical that many physicists refused to accept it for years. Einstein won the Nobel Prize in Physics for it in 1921, and it planted the seed of the concept that would come to define quantum mechanics entirely: wave-particle duality. Wave-particle duality is the experimental observation, replicated countless thousands of times, that every quantum object exhibits the properties of both waves and particles, and that which set of properties you observe depends on how you choose to look. The most famous demonstration of this is the double slit experiment. Imagine a barrier with 2 narrow slits in it. Shine light at the barrier. On the screen behind it, you observe an interference pattern, bands of light and dark created by the waves passing through both slits simultaneously and interfering with each other, exactly as water waves do when they pass through 2 gaps. This is wave behavior. Now close one slit. The interference pattern disappears. Open both slits again, but this time place detectors at each slit to record which slit each photon passes through. The interference pattern disappears again, even though both slits are open. The act of determining which path the photon takes destroys the interference. The photon, when observed, behaves as a particle traveling a single path. When not observed, it behaves as a wave passing through both paths simultaneously. This result is not a limitation of our instruments. It is not a consequence of our detectors disturbing the photons. It is something more fundamental. The quantum object genuinely does not have a definite path until it is observed. The act of measurement does not reveal a pre-existing property. It participates in creating the property it measures. This is the heart of quantum mechanics, and it troubled some of the greatest minds of the 20th century in ways that lasted their entire lives. Niels Bohr, the Danish physicist who more than anyone else shaped the early interpretation of quantum mechanics, expressed the situation this way: if quantum mechanics has not profoundly shocked you, you have not yet understood it. Werner Heisenberg discovered in 1927 what is now called the uncertainty principle. The principle states that there are pairs of physical properties that cannot both be precisely defined at the same time. The more precisely you know where a particle is, the less precisely you can know how fast it is moving and in which direction. And this is not a limitation of measurement. It is not that our instruments are too crude. It is that the particle genuinely does not have precise values for both properties simultaneously. The uncertainty principle is a mathematical consequence of the wave nature of quantum objects. A wave that is precisely localized in space contains contributions from an enormous range of frequencies and therefore momenta. A wave with a precise frequency is spread out across a large region of space with no definite position. You cannot have both. The universe will not allow it. Heisenberg's uncertainty principle
means that the classical picture of a particle as a tiny billiard ball sitting at a precise location, moving with a precise velocity, is simply wrong. Not approximately wrong, fundamentally wrong. Particles do not have precise positions and momenta at the same time. The universe, at its most basic level, is irreducibly fuzzy. The quantum state of a particle, its most complete possible description, is represented by a mathematical object called a wave function. The wave function encodes the probabilities of finding the particle at different locations, with different energies, with different spins, if a measurement is made. Before the measurement, the particle exists in a superposition of all these possible states simultaneously. After the measurement, the wave function collapses to a single definite value. Erwin Schrödinger, the Austrian physicist who developed the equation that describes how wave functions evolve over time, was deeply uncomfortable with this interpretation of his own mathematics. He invented a thought experiment to illustrate what he saw as its absurdity. Imagine a cat sealed in a box with a device that will release a lethal poison if a quantum event occurs, say, the decay of a radioactive atom. Before the box is finished, the atom is in a superposition of having decayed and not decayed. The quantum mathematics says this superposition should extend to everything connected to it: the detector, the poison, mechanism, and, if we are consistent, the cat itself. The cat is simultaneously alive and dead in a superposition of both states until the box is opened and the observation is made. Schrödinger intended this as a demonstration that the quantum interpretation must be incomplete. Instead, physicists took it seriously. The question of what actually happens when a quantum system interacts with a measuring device remains one of the deepest and most actively debated questions in all of physics. The Copenhagen interpretation, developed by Bohr and Heisenberg, argues that it is simply meaningless to ask what a quantum system is doing when it is not being measured. The wave function is a tool for calculating probabilities of measurement outcomes, not a description of objective reality. The many worlds interpretation, proposed by Hugh Everett in 1957, takes the opposite approach. It argues that the wave function never collapses. Instead, when a measurement occurs and multiple outcomes are possible, the universe branches into multiple copies, one for each possible outcome. Every quantum event that could have gone differently did go differently in a branch of the universe that continues to exist alongside our own. If the many worlds interpretation is correct, then right now, in an enormous number of parallel branches of the universe, everything that could have happened differently in your life did happen differently. Decisions you made, left unmade in other branches, events that occurred, absent in others. The quantum mechanical substrate of reality is constantly writing an infinite library of alternative histories, branching at every moment, at the scale of every atom. This is not science fiction. It is one of the serious, mathematically rigorous interpretations of quantum mechanics held by a significant fraction of working physicists. Quantum entanglement is perhaps the strangest feature of the quantum world, and the one that most disturbed Einstein, who called it spooky action at a distance, and spent years trying to prove it was impossible. When two quantum particles interact in certain ways, they can become entangled. Their quantum states become correlated in a way that persists no matter how far apart the particles subsequently travel. If you measure a property of one entangled particle, you instantaneously know the corresponding property of the other, regardless of the distance between them. The correlation is perfect, immediate, and not limited by the speed of light. Einstein, Boris Podolsky, and Nathan Rosen argued in 1935 that this could not be a fundamental feature of nature. In 1964, the physicist John Bell derived a mathematical theorem that made it possible to test experimentally whether hidden variables could explain quantum correlations. The experiments, beginning in the 1970s and culminating in a series of rigorous tests in the 2000s, gave a clear answer. The correlations predicted by quantum mechanics were observed. Bell's inequality was violated. Hidden variables of the classical kind do not exist.
The entanglement is real. What entanglement does not allow is faster than light communication. You cannot use entangled particles to send information at speeds exceeding light, because the correlations only become apparent when you compare measurements from both particles, and that comparison must travel through ordinary channels at speeds below light. The universe has arranged things so that entanglement is real, but cannot be used to violate relativity. Quantum tunneling is a phenomenon that should, by classical reasoning, be impossible. When a particle encounters a barrier through which it does not have enough energy to pass, classical physics says it cannot pass. But quantum mechanics says there is a non-zero probability that the particle will appear on the other side, as if it had tunneled through the barrier without ever having the energy to surmount it. This is not a theoretical curiosity, it is the mechanism by which the sun shines. Nuclear fusion in the core of the sun requires hydrogen nuclei to approach close enough to fuse. But the electromagnetic repulsion between positively charged nuclei creates a barrier that, by classical calculations, the nuclei do not have enough thermal energy to overcome. The fact that the sun shines, and has been shining for nearly 5 billion years, is a consequence of quantum tunneling. The nuclei do not have enough energy to climb over the barrier, they tunnel through it. Quantum tunneling also underlies the operation of the transistors in every electronic device you have ever used. The quantum world, in this sense, already runs the information age.
The vacuum of space is not empty. This is one of the most counterintuitive results of quantum field theory. The uncertainty principle, applied to energy and time, means that energy can briefly and spontaneously appear and disappear from what appears to be empty space. These transient fluctuations are called virtual particles, and they have measurable physical effects. The Casimir effect, predicted in 1948 and confirmed experimentally in 1997, is a force that arises between two uncharged parallel metal plates placed very close together in a vacuum. The force is attractive and measurable. Its cause is the quantum vacuum. The virtual particles that can exist in the space between the plates are constrained to certain discrete wavelengths. Outside the plates, all wavelengths are possible. The difference in the density of virtual particles inside and outside the gap creates a net inward pressure. Empty space is pushing the plates together. Quantum mechanics is not only the physics of atoms and subatomic particles, it is the physics of chemistry, and therefore the physics of life. The stability of atoms, the structure of the periodic table, the nature of chemical bonds, the specificity of molecular interactions, all of these are quantum mechanical phenomena. Electrons in atoms occupy discrete energy levels and can only change levels by absorbing or emitting a photon of precisely the right energy. This quantization of atomic energy levels is the reason the universe has chemistry, and therefore the reason the universe has biology. Photosynthesis, the process by which plants convert sunlight into chemical energy, appears to exploit quantum coherence. Experiments published in 2007 found evidence that the energy absorbed from photons travels through the molecular machinery of photosynthetic complexes through a quantum superposition of multiple pathways simultaneously. The energy explores all possible routes at once and finds the most efficient path with an effectiveness that classical models cannot fully explain. Birds may navigate using a quantum mechanical process in proteins in their eyes that is sensitive to the direction of Earth's magnetic field through the quantum property of electron spin. DNA mutations may be initiated by quantum tunneling of protons between the two strands of the double helix. The quantum world is not separate from the living world, it underlies it. Bose-Einstein condensation is a state of matter that occurs when a collection of particles is cooled to temperatures so close to absolute zero that the individual quantum wave functions of the particles overlap and merge into a single collective quantum state. The particles lose their individual identities. They behave as a single quantum entity, a macroscopic object described by a single wave function. This state was predicted by Satyendra Nath Bose and Albert Einstein in 1924 and 1925, but it was not produced in the laboratory until 1995. In a Bose-Einstein condensate,
quantum effects that normally manifest only at the scale of individual atoms become visible at the scale of macroscopic objects. The condensate can flow without friction. It can exhibit quantum interference patterns with itself. It behaves in ways that have no classical analog, as if a collection of millions of atoms had become a single quantum thing, occupying a single quantum state, moving as one. Quantum computing is the attempt to harness quantum mechanics for computation. A classical computer processes information in bits, each of which is either 0 or 1. A quantum computer processes information in quantum bits, called qubits, each of which can be in a superposition of 0 and 1 simultaneously. A system of n qubits can be in a superposition of 2 to the power of n states at once. Quantum algorithms can solve certain specific problems, including factoring large numbers and simulating quantum systems exponentially faster than any known classical algorithm. Most current internet encryption relies on the difficulty of factoring large numbers into their prime components. A sufficiently powerful quantum computer could break this encryption. Governments and technology companies are actively developing quantum-resistant cryptographic methods in anticipation of this possibility. The most fundamental question that quantum mechanics raises is not about any particular phenomenon. It is about the nature of reality itself. Classical physics assumed that the world exists independently of observers, that objects have definite properties whether or not anyone is measuring them. Quantum mechanics challenges this assumption in ways that have never been fully resolved. John Wheeler spent the later part of his career exploring the relationship between physics and information. He proposed that the universe might be fundamentally informational in nature, that physical reality arises from information in some deep sense that we do not yet understand. He summarized this vision with the phrase, "it from bit," suggesting that every element of the physical world derives its existence from answers to yes or no questions, from information. Quantum mechanics tells us that reality, at its most fundamental level, is not a collection of objects with definite properties existing independently of observation. It is a collection of potentialities, of probabilities, of superpositions that only resolve into definite outcomes when something interacts with something else. The act of observation is not a passive registration of a pre-existing fact. It is a creative act that participates in bringing the fact into existence. This is not mysticism. It is the conclusion of the most precisely tested scientific theory in history. The predictions of quantum mechanics have been confirmed experimentally to a precision of better than 1 part in 10 billion. No theory in the history of science has been more thoroughly tested. No theory has been more thoroughly vindicated, and yet no one fully understands what it means. Richard Feynman put it simply, nobody understands quantum mechanics. He did not mean that the theory was wrong or incomplete. He meant that the theory's mathematical machinery works with extraordinary precision, that its predictions are verified in every experiment, but that what it is telling us about the nature of reality is something the human mind, evolved to navigate a world of medium-sized objects moving at medium speeds, has not yet found a way to fully accommodate. Perhaps that accommodation will come. Perhaps a future theory, currently unimagined, will make sense of the quantum world in the way that Einstein's relativity made sense of the strange behavior of objects moving at near-light speeds. Or perhaps the strangeness is fundamental, a permanent feature of the gap between the universe's nature and the minds that evolved within it. Either way, the quantum world is there, beneath the solid, familiar surface of everything you can see and touch and know, buzzing with uncertainty, alive with superposition, riddled with entanglement, tunneling through barriers, fluctuating in the vacuum, waiting for the next interaction that will collapse another wave function and write another line in the universe's ongoing story of itself. Those were 100 quantum physics facts to fall asleep to, and now the mathematics fades. The wave functions dissolve back into the quiet from which they were summoned. The superpositions collapse, one by one, into the comfortable certainty of a dark room and a body growing heavier with sleep. But the quantum world is still there. In the atoms of the air around you, electrons are occupying their precise energy levels, descending from excited states and emitting tiny packets of light that you cannot see. In the synapses of your brain, ion channels are opening and closing, their behavior governed by the quantum mechanical properties of the proteins that form them. You are not separate from the quantum world. You are made of it. Every atom in your body is a quantum system. Every chemical bond that holds your molecules together is a quantum mechanical phenomenon. Every signal that travels through your nervous system exploits quantum properties of matter. You are, in the most precise and literal sense, a quantum mechanical object navigating a quantum mechanical universe. And tonight, while you sleep, those quantum systems will continue their ancient work. The electrons in your neurons will jump between states. The proteins in your synapses will fold and unfold according to quantum rules. The molecules that carry the memories of this day will be sorted and stored and connected to the larger fabric of everything you have ever known. The universe does not stop being strange while you sleep. It simply lets you rest. Let your breathing slow. Let the uncertainty settle into something like peace. Science for Sleep will be here when you return.